Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the realm of astronomical anomalies. Those strange moments when our telescopes capture something that doesn't quite fit. When pixels arrange themselves in patterns that whisper of mysteries we haven't yet learned to ask about properly. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. There exists, in the archives of astronomical observatories scattered across Earth's surface and orbiting in the silence above its atmosphere, a collection of images that occupy a peculiar category. They are not errors, exactly, though they contain elements that resemble instrumental failure. They are not discoveries, precisely, though they sometimes become discoveries years after their initial recording. They rest in a liminal space between malfunction and revelation, between the noise inherent in all observation and the signal that carries meaning across billions of kilometers of emptiness. These are the glitch images, the frames that shouldn't exist in the form they take, the data that passes every technical validation check while simultaneously defying the models built to interpret it. A charge-coupled device aboard a space telescope accumulates photons across its silicon substrate. Each pixel functions as a microscopic well, gathering individual particles of light that departed their source perhaps when Earth's continents occupied different positions on the globe, when different species walked its forests, when the star itself burned with minutely different luminosity. The photons arrive, they register. The charge accumulates in precise, quantifiable increments, and sometimes, very occasionally, the pattern they form makes no immediate sense. The human eye evolved to detect motion in grasslands and judge distances to water sources, now examines arrays of numerical values translated into grayscale or false color. A contemporary astronomer scrolls through image sequences on a monitor in a temperature-controlled room, searching for the subtle. A galaxy's core that brightened by 3% over 6 months. A stellar occultation lasting 14 seconds. The gradual drift of a main belt asteroid against the fixed background of more distant stars, but also the unexpected spike. The pixel cluster that glows with intensity uncorrelated to any catalogued object. The moving point source that appears in 3 consecutive frames, then vanishes, leaving no trace in archival data from the same coordinates captured a week prior or a week hence. The scientific method requires reproducibility. Astronomical observation, by its nature, often denies this requirement. The universe does not repeat its experiments on human timescales. A supernova explodes once per galaxy per century, on average. An asteroid tumbles through its closest approach to Earth on a trajectory that will not recur for 10,000 years. And an interstellar object, arriving from the space between stars, passes through the inner solar system perhaps once per human lifetime. If we are fortunate, if our instruments happen to be looking in the correct direction, if the object's albedo and size place it within the detection threshold of our surveys, these visitors do not announce themselves in advance, they simply appear. Already departing. In the spring of 2020, as human civilization navigated its own disruptions, a comet designated C2019Y4 Atlas began to disintegrate approximately 146 million kilometers from the Sun. This distance places it well beyond Earth's orbit, in a region where cometary ice sublimates gently, where solar radiation pressure exerts steady but manageable force on dust grains liberated from the nucleus, Comets fragment. The phenomenon, while dramatic, falls within expected parameters. Thermal stress fractures the nucleus. Volatile pockets outgas asymmetrically. The structural integrity, never robust, fails. The object that was one becomes many. A dispersing cloud of rubble following the orbital path established by the parent body. But Atlas, fragmented in a manner that generated images, captured by the Hubble Space Telescope during dedicated observation sequences, showing structures that persisted longer than models predicted. Fragments maintain cohesion when calculations suggested they should sublimate or further subdivide. Brightness variations occurred in patterns that implied rotation rates inconsistent with the piece's estimated sizes and shapes. The images existed. The data underwent standard reduction procedures. Cosmic ray hits were identified and masked. Flat field corrections compensated for pixel-to-pixel sensitivity variations. Background stars were subtracted. What remained was light genuinely reflected from fragments of a disintegrating comet nucleus. And yet, the fragments behaved slightly, persistently wrong. This wrongness measures in percentages. A rotation period 7% longer than predicted. A fragment brightness 12% dimmer than its estimated cross-section should produce. Deviations small enough to attribute to model limitations, to uncertainties in assumed density or albedo or composition. Small enough to ignore, except that astronomers, as a professional community, find ignoring small deviations uncomfortable. Small deviations compound. They accumulate into paradigm shifts, given sufficient time and attention. The perihelion precession of Mercury, a tiny discrepancy in an otherwise Newtonian solar system, eventually required general relativity for its explanation. No one suggests that fragmenting comets require new physics, but the images remain, stored in archives, available for reanalysis as models improve, as computational methods evolve, as future researchers develop questions that current researchers have not yet formulated. The pixel arrays preserve information that exceeds current interpretive capacity. They contain answers to questions not yet asked. This represents a peculiar form of temporal displacement, data waiting patiently in digital storage for theory to catch up, for context to emerge, for the specific combination of curiosity and technique that will render the anomalous comprehensible. In a facility in Maryland, the Hubble Space Telescope transmits data to ground stations at a rate of approximately 1 megabit per second during contact windows. The stream arrives as packets, checked for transmission errors, assembled into complete frames, distributed to researchers who requested the observation time. The telescope itself, orbiting at an altitude of 547 kilometers, maintains attitude control with reaction wheels and gyroscopes, pointing its aperture at designated coordinates with arc-second precision. It does not know what it observes. It cannot distinguish a comet from a galaxy, a supernova from a cosmic ray strike on its detector. It simply gathers photons, converts them to electrical charges, digitizes the charges, and broadcasts the results earthward. The interpretation, the meaning-making, occurs elsewhere. In minds evolved for pattern recognition, now trained to recognize patterns in data streams representing wavelengths the human retina cannot detect, timescales the human experience cannot naturally encompass, distances for which terrestrial intuition provides no useful calibration, and sometimes those minds encounter patterns that resist interpretation, images that contain no obvious error but equally no obvious explanation, data that exists in the uncertain space between malfunction and mystery. The glitch images accumulate quietly, one observation at a time, across decades of astronomical survey work. They rest in databases, annotated with flags indicating further analysis required, or preliminary results inconclusive, or awaiting theoretical framework. They represent the patient work of documentation proceeding even when understanding lags behind observation. They are, in their way, a form of gift to future science. Our archive of anomalies, preserved against the possibility that what seems inexplicable now might prove foundational later, might contain the seed of some conceptual revolution not yet imaginable from within current paradigms, or they might simply be glitches, artifacts of instrumental limitations, patterns that mimic significance while conveying none. The universe does not label its mysteries. It simply presents phenomena and waits, with the infinite patience available to processes operating on timescales measured in billions of years, for observation to accumulate into comprehension. The telescope continues its orbit. The data continues to flow, and somewhere in the archive, pixels hold their light, unchanged, awaiting interpretation. Light departs a distant galaxy when Earth's surface still hosts dinosaurs, when the Atlantic Ocean measures narrower by several hundred kilometers, when the position of stars in the night sky differs subtly from their contemporary arrangement. The photons cross intergalactic space at their constant velocity, undiminished, carrying information encoded in wavelength and polarization about the conditions of their emission. They arrive at a charge-coupled device on a telescope mirror 4 billion years later, striking silicon atoms, liberating electrons, creating measurable charge in rectangular wells arranged in a grid pattern, and sometimes, in the same moment, a cosmic ray also arrives. These are not photons, but particles, protons primarily, accelerated to relativistic velocities by supernova shockwaves or active galactic nuclei, spiraling through magnetic fields that thread the galaxy. They carry far more energy than visible light photons. When one strikes a CCD, it doesn't deposit charge in a single pixel, but cascades through the detector substrate, creating a track of saturated pixels that resembles a small streak or cluster to the uninitiated eye. Examining the raw image, this track might appear to be a faint star, a distant quasar, an asteroid captured mid-transit across the field of view. The early observers, working with photographic plates rather than digital detectors, encountered different artifacts, emulsion flaws, processing chemical residue, scratches on glass. Each generation of instrument introduces its characteristic errors, its signature malfunctions that observers must learn to recognize and exclude. The CCD revolutionizes astronomy beginning in the 1970s, offering quantum efficiency far exceeding photographic emulsion, linear response across a wide dynamic range, and digital output amenable to computational analysis. It also introduces new artifact categories, hot pixels that register charge even in darkness, due to defects in the silicon crystal structure, charge bleeding when a bright star saturates its pixels and overflows into adjacent wells, and cosmic ray hits, thousands per hour in space-based telescopes, each creating a false signal that must be identified and removed. The process of removing them, cosmic ray rejection, relies on redundancy. The same field gets imaged multiple times. Pixels that show high values in only one exposure likely contain cosmic ray contamination. Software compares frames, identifies outliers, masks them, combines the clean pixels from multiple exposures into a final image. Except when the cosmic ray hit coincides with a real transient event, a supernova beginning its brightness increase, a variable star at maximum luminosity, an asteroid moving against the background stars, appearing in a different position in each frame. The algorithm, following its programmed logic, might reject the real astronomical event as apparent noise. The discovery gets masked away. The photons that traveled billions of years to reach the detector get classified as artifact and excluded from the final image. This happens rarely, but not never. Automated survey telescopes image millions of square degrees of sky per night, generating terabytes of data, Far exceeding human capacity for individual frame inspection, machine learning algorithms now perform initial classification, flagging candidates for human review. The algorithms achieve high accuracy, 98%, 99% in optimal conditions, but the remaining 1 or 2% contains everything that doesn't fit current categories, every genuinely novel phenomenon, every object type not yet discovered and therefore not included in the training set, and every imaging artifact that happens to mimic. Through pure coincidence, the characteristics of something real. A researcher at the European Southern Observatory examines a flagged image showing a point source that brightened by a factor of 10 over 6 hours. The location contains no catalogued variable star, no known active galactic nucleus. The spectrum, automatically extracted, shows features consistent with thermal emission from a cooling object. Further investigation reveals the brightening occurred in only one of the 3 filters used that night. The other 2 filters show nothing unusual at the same coordinates. This suggests instrumental error, perhaps a reflection or electronic noise in one CCD channel. But thermal emission should appear across multiple wavelengths. Its absence in the other filters contradicts the spectral identification. The researcher requests follow-up observations. The telescope schedules time 3 nights later, pointing again at the same coordinates. The object has vanished. The field appears identical to archival images from years prior. No source, variable or otherwise, exists at that location above the detection threshold. The event gets catalogued as unconfirmed transient, probable instrumental artifact. The data remains in the archive, available for future analysis, but receives no further immediate attention. 5 years later, a different researcher, investigating a different phenomenon, perhaps constructing a catalogue of short-duration transients or studying instrumental systematics in survey data, encounters this same event in the archive, equipped with improved models of CCD behavior or new understanding of a particular class of astronomical transient. This researcher recognizes a pattern, or doesn't. The mystery persists. Only took 4 billion years for the light to arrive, and a few microseconds of electronic noise to render its message ambiguous. The irony rests quietly in the archive, neither forgotten nor resolved. Meanwhile, cosmic rays continue to strike detectors at their characteristic rate. Determined by solar activity cycles and the spacecraft's location relative to Earth's magnetosphere, each hit creates a small explosion of liberated charge. Each gets recorded. Each requires identification and removal. The patience required for this work, examining millions of images, applying consistent criteria, maintaining vigilance for the genuinely novel while filtering the repetitively artifactual, resembles a form of meditation. The eye learns what to ignore. The mind develops pattern recognition tuned to specific anomaly types, and occasionally, very occasionally, something appears that doesn't match any known pattern. That resists categorization. That exists in the uncertain space where careful observation meets the limits of current understanding. These images get set aside, not discarded. Astronomy maintains long memory. Data storage costs decrease exponentially with time. What seems inexplicable today might become routine tomorrow. Once theory advances, once a new object class gets discovered and characterized, the photons that arrived wrong, or arrived correctly but encountered interpretation at the wrong moment in the development of astronomical knowledge, wait in their digital storage, unchanged by time, ready to be re-examined whenever human curiosity returns to them. The cosmic rays continue their bombardment. The CCDs continue their accumulation. The archive grows, and somewhere in that growth, in the patient accumulation of observations, both understood and mysterious, rests the possibility that yesterday's glitch becomes tomorrow's discovery, simply requires waiting. And looking again, the universe appears willing to wait, In December 2019, an automated survey telescope in Hawaii detects a new comet. The discovery itself follows routine procedure. A moving object appears in consecutive frames, its motion consistent with solar system orbit, its position not matching any catalogued asteroid or comet. Software flags it for human verification. An astronomer confirms the detection. The object receives designation C2019Y4 with ATLAS appended to honor the Asteroid Terrestrial Impact Last Alert system that found it. Initial observations suggest nothing exceptional. The orbit calculation indicates a long-period comet, perhaps visiting the inner solar system for the first time in millennia, following an elliptical path that will bring it relatively close to both Sun and Earth during spring 2020. Comets brighten as they approach the Sun, their ices sublimating, their coma expanding. Atlas follows this pattern, growing brighter through January and February as predicted. Observers worldwide add it to their monitoring programs. Photographers attempt long exposure captures as the comet becomes visible to larger amateur telescopes. Then, in late March, the brightening curve changes character. Instead of the smooth increase expected from a growing coma, Atlas begins fluctuating, brightening sharply, then dimming, then brightening again. The variations occur over days, too rapid for orbital mechanics, too slow for rotation of a nucleus. Spectroscopic observations reveal changes in the gas production rate, in the relative abundances of different molecular species in the coma. By early April, observers report the comet appears elongated in images, not the smooth, circular coma of a healthy comet, but a stretched, irregular cloud. Atlas is fragmenting. The Hubble Space Telescope receives directors' discretionary time to observe the disintegration in unprecedented detail. On April 20th and April 23rd, Hubble images the comet system across multiple wavelengths. The Wide Field Camera 3, operating in visible light, resolves approximately 30 distinct fragments embedded in the expanding debris cloud. The fragments arrange themselves along the comet's former orbital path, each following the same trajectory through space, separated by minutes or hours of travel time. The largest pieces measure perhaps 100 meters across, estimates derived from brightness and assumed albedo. The smallest resolved fragments approach the telescope's resolution limit. Between them spreads dust, gas, debris too small to resolve individually, but visible as diffuse haze connecting the fragments. What surprises observers is not the fragmentation itself, but the coherence of certain fragments. Standard models predict that once a comet nucleus fractures, the exposed interior ice sublimates rapidly. The increased surface area accelerates the comet's self-destruction. Fragments should either dissipate within days or undergo further splitting as thermal stress continues to affect their structure. Several of Atlas's fragments persist through multiple observation epochs, maintaining their brightness, their apparent size, their existence as discrete objects rather than dissolving into the general debris field. Fragment B, in particular, remains visible in Hubble images separated by 3 days. Its brightness varies slightly, consistent with rotation bringing different surface areas into sunlight, but its overall luminosity suggests a relatively stable chunk of material resisting the sublimation that should be destroying it. Calculations of Fragment B's rotation period, derived from its brightness variations, yield a value of approximately 6 hours. This duration seems too slow for the fragment's estimated size. A 100-meter ice and dust rubble pile, held together primarily by its own minimal gravity, should spin faster. Rotation periods of hours to tens of minutes appear more typical for objects this small, unless the fragment is larger than brightness suggests, or denser, or its albedo differs from assumed values, or the models contain subtle errors in how they treat the thermal evolution of fragmenting cometary nuclei. The uncertainty is small, the discrepancy measurable, but not dramatic. No one proposes revolutionary physics to explain why fragment B rotates slower than predicted. But the image exists, a chunk of ancient ice and dust, older than Earth's oceans. Formed in the outer solar system billions of years ago, now disintegrating 146 million kilometers from the Sun, captured in exquisite detail by a telescope orbiting Earth. And that chunk behaves 3% differently than models predict. 3% might be noise, measurement uncertainty, model oversimplification, or it might indicate something genuinely unaccounted for in current understanding of cometary structure, composition, thermal properties. The data cannot, by itself, distinguish these possibilities. By May, Atlas has completely dispersed. The fragments continue fading as they sublime away. Ground-based observers lose the comet below their detection thresholds. It becomes a ghost, a dispersing cloud of debris no longer coherent enough to track as a single object. The Hubble images remain. Astronomers publish papers analyzing the fragmentation sequence, the fragment size distribution, the gas production rates. They compare Atlas to other fragmenting comets, Shoemaker-Levy 9, Linear, Schwarzmann-Wachsmann 3. They refine models of cometary structure, incorporating Atlas's observed behavior. The 3% rotation discrepancy gets mentioned in a table of measured parameters, footnoted with possible explanations, but not elevated to primary focus. Too small, too uncertain, too easily dismissed as the kind of minor mismatch between observation and theory that pervades all astronomical measurement. And yet, the image persists. Fragment B tumbling slowly through space, sublimating, dissolving, but doing so according to a timeline slightly offset from expectation, a glitch in the smooth narrative of cometary death, a pixel pattern that fits almost perfectly, except for that small, persistent wrongness. The comet that fragmented exactly when thermal stress models predicted, but whose pieces refused to behave entirely according to script, only took 4.5 billion years to form and 3 months to disintegrate, and we caught 25 of those days on camera. The fragments now orbit the Sun as dust, indistinguishable from the zodiacal cloud, the diffuse debris that fills the inner solar system. Particles that were once part of Comet Atlas join particles from 1,000 other dead comets, slowly spiraling sunward under pointing Robertson drag, destined for eventual vaporization. But for 3 days in April 2020, Fragment B existed as a discrete object, rotating slowly, reflecting sunlight, registered by a CCD as a pattern of brightness values that didn't quite match prediction. The universe kept the fragment intact just long enough for documentation, then allowed it to dissolve. A small kindness, perhaps, or simply the random distribution of thermal stress fractures in primordial ice. The Hubble Space Telescope moves on to its next scheduled observation. The archive grows by another dataset, and Fragment B continues its slow tumble into non-existence, unobserved. Comets emit light through 2 mechanisms. Reflected sunlight bounces from dust particles in the coma and tail, producing a continuous spectrum across all wavelengths, white light scattered by microscopic grains of silicate and carbon. But comets also glow through fluorescence, as solar ultraviolet radiation excites molecules sublimating from the nucleus, causing them to emit at characteristic wavelengths specific to their atomic composition. Sodium glows bright yellow at 589 nanometers, the D-line doublet. Familiar from streetlights, from chemistry demonstrations, from the element's ubiquitous presence in terrestrial experience, cometary sodium tails form when sodium atoms, liberated from dust grains by solar radiation or sputtering processes, get ionized and swept into tails by solar wind and radiation pressure. These tails glow in monochromatic yellow, extending sometimes millions of kilometers behind the nucleus. Visible in specialized narrowband imaging, most comets produce detectable sodium emission. The abundance varies, some show strong sodium tails, others weak, but the phenomenon itself qualifies as routine. Expected, catalogued across hundreds of observed comets. CT 2019. Wow. 4. Atlas produced sodium emission that behaved strangely. Ground-based observatories monitoring Atlas in late March 2020 noticed the sodium tail brightening disproportionately as the comet fragmented. Not simply growing brighter in proportion to increased surface area, that would be expected as fragmentation exposed fresh material, but brightening more than models predicted based on the comet's overall gas production rate. The ratio of sodium emission to other spectral lines, particularly the CN and C2 bands that serve as standard measures of cometary activity, exceeded typical values by factors of 2 to 3. This suggests Atlas possessed unusually high sodium abundance in its nucleus. Comets form from the same primordial material that built the solar system, but local variations in that material's composition, differences in temperature, pressure, radiation environment during formation, produce comets with varying elemental ratios. A sodium-rich comet indicates formation in a region of the protoplanetary disk where sodium condensation occurred efficiently, where temperature conditions allowed sodium-bearing minerals to incorporate into the growing comet nucleus. Except Atlas's orbit suggests formation in the Oort cloud, the distant reservoir of comets surrounding the solar system at tens of thousands of astronomical units. The Oort cloud formed from material ejected from the inner solar system during planetary migration, mixed with material captured from the Sun's natal star cluster. Comets from this reservoir show diverse compositions, reflecting the varied source regions that contributed to the cloud. But extreme sodium enrichment remains unusual even accounting for this diversity. The spectroscopic data exists, multiple independent observations from different telescopes, using different instruments, all recording sodium emission lines stronger than expected relative to other spectral features. The interpretations diverge. Perhaps Atlas incorporated material from an unusually sodium-rich pocket of the protoplanetary disk. Perhaps its parent body underwent differentiation, concentrating sodium in certain regions, and the nucleus that eventually became Atlas derived from one of these enriched zones. Perhaps the measurement uncertainties are larger than calculated, and the apparent anomaly reflects systematic error in calibration or background subtraction. Or perhaps something about the fragmentation process itself, the sudden exposure of interior material, the changing geometry of gas emission, the thermal evolution of freshly exposed surfaces, creates conditions where sodium emission gets enhanced through mechanisms not fully captured in standard models. The sodium atoms continue their existence indifferent to these competing explanations. They absorb solar photons at 589 nanometers, re-emit them in random directions, get ionized by ultraviolet radiation, accelerate under solar wind pressure, eventually join the interplanetary medium. They do not know they constitute an anomaly. A researcher at the Lowell Observatory analyzes spectra from March 29th, comparing sodium line strength to contemporaneous measurements of OH emission, hydroxyl radicals produced by water ice sublimation. The ratio Na-OH equals 0.043, approximately triple the median value for long-period comets in the existing database. The measurement uncertainty spans plus or minus 30%, large enough to potentially bring the value into agreement with other comets, if the true value lies at the low end of the uncertainty range, but the central value remains elevated, anomalously high. The researcher includes the measurement in a paper submitted to the Astrophysical Journal. The paper focuses on Atlas's fragmentation dynamics, with the sodium abundance discussed in a subsection titled Composition and Gas Production Rates. The anomalous sodium receives 3 paragraphs of discussion, followed by acknowledgement that additional observations would be needed to confirm the enhancement and constrain its physical origin. The comet, by the time the paper appears in print 6 months later, has fully dispersed. Additional observations are impossible. The sodium atoms that produce those anomalous spectral lines now drift through interplanetary space, individually untrackable, merged with the general population of solar system sodium, atoms from countless other comets, from asteroid collisions, from solar wind interactions with planetary atmospheres. The evidence for their unusual abundance exists only in archived spectra, in calibrated intensity measurements stored as numerical tables in journal supplementary materials. Future researchers, constructing catalogues of cometary composition, will include Atlas as a data point. Its sodium abundance will appear as an outlier in distribution plots, annotated perhaps with a question mark or a note about measurement uncertainty, or it will inspire investigation into what physical processes might generate sodium enhancement. Perhaps laboratory experiments recreating cometary ice under various formation conditions. Perhaps numerical simulations of protoplanetary disk chemistry in different radial zones, or it will remain simply a curiosity, an unexplained measurement, a comet that glowed yellow slightly brighter than expected for reasons not definitively established. The sodium atoms themselves, distributed now across cubic kilometers of space, continue absorbing and emitting light according to quantum mechanical principles established in the first minutes after the Big Bang. Indifferent to whether human observers find their collective behavior surprising, only took 4.5 billion years to form, and we observed them for 6 weeks. And they glowed 3 times brighter than they should, and we will probably never know exactly why. The spectrum remains in the archive. The yellow light, now absent from the actual sky, persists as data, numbers in a table. A curve on a graph showing emission intensity versus wavelength, with one peak notably higher than models predict, a glitch in the expected composition, a chemical signature that doesn't quite fit. The fragmentation continued. The sodium emission faded as the comet dispersed. Observations ceased. And the anomaly transitioned from active mystery to archived curiosity, awaiting the moment, if it comes, when theory advances enough to render the unexpected comprehensible. The universe continues its chemistry, indifferent to documentation. On October 19, 2017, a telescope in Hawaii operated by the Pan-STARRS survey detects an object moving rapidly through the inner solar system. Initial trajectory calculations indicate something impossible. The object arrived from interstellar space. The orbital eccentricity, a parameter measuring how elliptical an orbit is, exceeds 1.0. This means the path is not elliptical but hyperbolic. The object is not bound to the Sun's gravity. It approached from the direction of the constellation Lyra, passed within 0.25 astronomical units of the Sun at perihelion, and is now departing, accelerating back toward interstellar space. Under the gravity assist from its close solar passage, it receives designation 1. I/Oumuamua, the first recognized interstellar object, the one eye denoting this historic status, the Hawaiian name meaning scout or messenger. For astronomers worldwide, this represents a moment comparable to first contact, not with intelligence, but with matter from beyond the solar system's boundary, from another star's domain. Every previous comet, asteroid, and debris fragment studied across 4 centuries of telescopic observation originated in the Sun's family. This object, formed around a different star, was ejected by gravitational interactions into the galaxy's general stellar population, drifted for millions or tens of millions of years through interstellar space, and happened to pass close enough to Earth for detection. The probability of detection depends on 2 factors: how many interstellar objects pass through the inner solar system per year, and how sensitive our surveys have become. Pan-STARRS, operational since 2010, scans the sky repeatedly, detecting ever fainter objects, but Oumuamua was already receding when discovered, already fading. Visible only for a few weeks before dropping below detection thresholds. The window for observation measures in days, not months or years. Telescopes worldwide abandon scheduled programs. Time gets allocated for spectroscopy, photometry, imaging, any observation that might characterize this visitor before it escapes beyond reach. The object itself appears tiny, perhaps 100 meters long, tumbling chaotically, its brightness varying by a factor of 10 over a rotation period of approximately 8 hours. This brightness variation suggests extreme elongation. An object spinning about its long axis would show minimal brightness changes. An elongated object tumbling end over end would periodically present different cross-sections to observers, creating the observed brightness variations. Analysis suggests an axis ratio of roughly 10. 1. An extremely elongated shape, like a cigar, or perhaps a pancake viewed edge-on at some rotation phases. No natural solar system object exhibits such extreme elongation. Asteroids typically show axis ratios below 3. 1. The most elongated objects, certain binary contact asteroids, or fragments from catastrophic collisions, might reach 4, 1, or 5, 1, but 10, 1 exceeds any known natural example, except Oumuamua exists. The brightness variations occur. The data requires explanation. Perhaps interstellar space sculpts objects differently than the gentler environment within planetary systems. Perhaps collisions in dense stellar environments produce different fragment size distributions. Perhaps Oumuamua represents a fragment from a larger body, sheared off along a preferential plane during some ancient impact, now tumbling solo through the galaxy. Or perhaps the axis ratio calculation contains systematic errors. Perhaps the object's surface has albedo variations, bright patches and dark patches, that mimic geometric shape variations. Perhaps it's not as elongated as the simple brightness model suggests. The spectrum offers limited insight. Oumuamua appears reddish. Consistent with organic-rich surfaces common on outer solar system objects, but also consistent with many other composition types. The spectrum lacks features diagnostic of specific minerals or ices. It resembles a generic space rock spectrum, telling observers little about formation conditions or internal composition. No coma appears, no tail, no dust emission. These absences rule out significant ice content on the surface. An interstellar comet, entering the sun's warmth after millions of years at near absolute zero temperatures, should sublime dramatically, but Oumuamua remains inert, rocky, apparently dead. This suggests formation in a rocky zone analogous to our solar system's asteroid belt, an interstellar asteroid rather than interstellar comet, except asteroids should not exhibit such extreme elongation. The imaging continues. Multiple telescopes track Oumuamua as it recedes. Photometric measurements accumulate, refining the rotation period, confirming the brightness variations, attempting to constrain the three-dimensional shape. And then someone notices an anomaly in the trajectory. The object is accelerating slightly as it recedes from the sun, not decelerating under the sun's gravity as expected, but experiencing a small additional outward force. The acceleration measures tiny, approximately 5 times 10 to the negative 9th meters per second squared, minuscule, but detectable through careful analysis of positional measurements over weeks. Comets experience non-gravitational acceleration from outgassing, sublimating ice jets material preferentially from the sunlit hemisphere, creating rocket-like thrust that perturbs the orbit. The effect is well documented, routinely measured in active comets, but Oumuamua shows no outgassing signature, no coma, no detected gas emission in any wavelength. So what provides the acceleration? Perhaps outgassing occurs at levels too low for direct detection, but sufficient to create measurable thrust. Perhaps the surface contains a thin veneer of ice that sublimates without creating visible coma. Perhaps the object rotates such that outgassing jets, if they exist, average out in brightness but not in net thrust. Or perhaps the interpretations fracture into speculation. Solar radiation pressure acting on a very low-density, highly porous object, interaction with the solar wind under exotic surface conditions. Even, briefly, suggestions of artificial origin, a light sail, a probe from another civilization. The speculation dies quickly, not from proof of natural origin, but from absence of evidence for artificiality. Occam's razor favors natural explanations when available. The universe contains countless asteroids and comets. Interstellar space presumably hosts even more. Ejected from billions of planetary systems, one eventually passes close enough for detection. That it behaves slightly strangely does not require extraordinary explanations. Simply requires patience with incomplete data, with the limitations of observing an object too small, too distant, receding too rapidly for comprehensive characterization. By January 2018, Oumuamua has faded beyond detection capability of even the largest telescopes. It continues its journey outward, toward the constellation Pegasus, destined to wander interstellar space indefinitely. The data remains. Dozens of published papers analyze the observations from every conceivable angle: the axis ratio, the acceleration, the spectrum, the rotation, the consensus conclusions. Probably natural. Definitely strange. Insufficiently observed. Only took millions of years to travel from another star, and we had 3 weeks to study it, and it left more questions than answers. The images, grainy. The object appearing as a faint dot even in the best exposures, show nothing visually remarkable, just a point source, barely distinguishable from background stars except for its motion. But that point source contains photons reflected from a surface that formed around another sun, traveled interstellar distances, and briefly intersected humanity's moment of technological capability for detection. A glitch in the solar system's family portrait. A visitor that shouldn't exist yet does. The archive grows. The mystery persists. The acceleration of Oumuamua emerges not from direct measurement during observation, but from archival analysis performed months after the object faded from view. Researchers at the European Space Agency, calculating the object's precise trajectory using all available positional measurements, notice that purely gravitational models fail to predict Oumuamua's position accurately. The discrepancy grows over time. By late November 2017, the observed position deviates from the predicted position by amounts exceeding measurement uncertainty. The object has traveled slightly farther from the Sun than gravity alone would allow. This requires an additional outward force. The acceleration vector points approximately radially away from the Sun, declining with distance in a manner consistent with decreasing solar flux. For comets, this signature indicates outgassing. Water ice sublimates, creating jets of vapor that push the nucleus. The thrust varies with solar distance because sublimation rate depends on temperature, which depends on solar heating. But Oumuamua displayed no detectable outgassing during observation. The paper quantifying the acceleration, published in Nature in June 2018, includes extensive analysis ruling out alternative explanations. Solar radiation pressure, photons transferring momentum to the object's surface, produces acceleration orders of magnitude too small unless Oumuamua possesses impossibly low density or impossibly high surface area to mass ratio. Interaction with the solar wind, charged particles flowing outward from the Sun, similarly produces insufficient force. Measurement error cannot explain the effect. Multiple independent astrometric observations from different observatories show consistent deviations from gravitational predictions. The authors conclude that outgassing provides the most physically plausible explanation. even absent direct detection of cometary activity. Perhaps the outgassing involves less common volatiles, nitrogen, carbon monoxide, hydrogen, rather than water. Perhaps the gas production rate lies below detection thresholds while remaining sufficient for measurable thrust. The conclusion satisfies most researchers. It invokes known physics, previously observed phenomena, straightforward extrapolation from better studied cases. But a minority asks, if we cannot detect the outgassing that supposedly explains the acceleration, do we truly understand what occurred? Or have we simply applied the label outgassing to an anomalous measurement, declaring the mystery solved because we possess a word for it? The question rests uneasily in the literature. Not quite skepticism, not quite acceptance. A persistent discomfort with explaining an unobserved phenomenon by invoking a different unobserved phenomenon. The numbers exist. Positional measurements from October through December 2017 recorded to sub-arc-second precision, showing Oumuamua deviating from a purely ballistic trajectory by approximately 40,000 kilometers over 2 months. The physics exists. Conservation of momentum requires that deviation to result from force. Solar gravity pulls inward. Something else must push outward. The gap exists between the force required and the observational evidence for that force's source. Into this gap flows interpretation, modeling, assumption, the application of knowledge from other contexts, cometary behavior, volatile sublimation physics, gas dynamics in vacuum, to an object observed incompletely under unique circumstances. The interpretation might be correct. Probably is correct. Outgassing explains non-gravitational acceleration in dozens of comets. The principle applies straightforwardly to Oumuamua despite detection limitations. But probably correct differs from definitively established. The distinction matters at the boundary of knowledge, where observation meets the unknown. A researcher at Harvard proposes an alternative. Perhaps Oumuamua is a light sail, an artificial structure designed to accelerate under radiation pressure. The paper, published in the Astrophysical Journal Letters, performs calculations showing that a sufficiently thin reflective sheet, thickness measured in millimeters or less, would experience radiation pressure acceleration matching observations. The scientific community reacts with skepticism, not because light sails are physically impossible, they're not, but because invoking artificial origin requires extraordinary evidence. The hypothesis multiplies assumptions. Not only must an extraterrestrial civilization exist, it must build interstellar probes. Those probes must survive millions of years in interstellar space. And one must happen to pass through our solar system during the brief window when human technology can detect it. Occam's razor favors simpler explanations. A rock outgassing requires fewer assumptions than an alien artifact. The light sail hypothesis joins the literature not as accepted explanation, but as boundary marker, indicating the range of physically possible interpretations compatible with observations. The intellectual space between definitely outgassing and definitely artificial contains the actual epistemic state, uncertain, awaiting additional data that will never arrive because the object has departed. Only took 40 million years to cross from another star, and we tracked it for 10 weeks, and its trajectory deviated by 40,000 kilometers, and we measured that deviation to within 10%, and we still cannot definitively explain what caused it. The irony accumulates quietly in the archive. Meanwhile, Oumuamua continues outward, accelerating under whatever process produces the force, whether outgassing or radiation pressure or something unconsidered. The force diminishes as solar intensity decreases with distance. By 2019, the object has moved beyond the orbit of Jupiter. The acceleration becomes unmeasurably small, but it continues. Photons still strike the surface. Volatiles, if present, still sublime in trace amounts. Momentum transfers infinitesimally, pushing the object marginally faster along its trajectory. By 2025, Oumuamua has crossed beyond Saturn's orbit, invisible to any telescope, traveling at approximately 26 kilometers per second relative to the Sun. In approximately 20,000 years, it will exit the solar system entirely, returning to interstellar space from which it came. No human instrument will ever observe it again. The data set is complete, final, immutable, and ambiguous. The measurements exist in the archive, right ascension and declination recorded to fractions of an arc-second, photometric brightness logged across multiple wavelengths, spectra showing reddish reflectance with no diagnostic features, all of it preserved digitally, available for reanalysis by anyone with interest and appropriate software. But the object itself, the physical reality of rock or ice or whatever material comprises Oumuamua, has passed beyond reach, beyond follow-up observation, beyond the possibility of resolution. What remains is interpretation, competing models, Bayesian probability assessments of different scenarios, the accumulated weight of expert opinion leaning toward outguessing while acknowledging uncertainty, and one anomalous trajectory, documented to high precision, showing acceleration that requires explanation, a glitch in the expected motion, a deviation from pure gravity. The universe permitted observation of the deviation, but withheld observation of its cause. A small mystery. In the grand catalogue of cosmic unknowns, an object approximately 100 meters long, now several billion kilometers from Earth, receding at escape velocity, carrying its secrets back to the interstellar medium. The archive preserves its trajectory. The questions persist, and human observers, briefly granted glimpse of matter from another star's domain, return attention to the solar system's native population, to objects that orbit predictably, that return periodically, that permit extended study. Oumuamua continues its journey, unobserved, indifferent. On August 30th, 2019, amateur astronomer Gennady Borisov, operating a 0.65-meter telescope in Crimea, detects a comet-like object showing apparent motion inconsistent with solar system membership. Follow-up observations by professional observatories confirm the trajectory. Orbital eccentricity approximately 3.4, clearly hyperbolic, clearly interstellar in origin. The object receives designation 2I/Borisov, the second recognized interstellar object, discovered remarkably only 2 years after Oumuamua, suggesting these visitors pass through the inner solar system more frequently than previously estimated. But, unlike Oumuamua, Borisov behaves like a comet. Spectroscopy immediately detects CN emission, cyanogen radicals fluorescing in sunlight, diagnostic of volatile sublimation. A visible coma surrounds the nucleus. A faint tail extends anti-sunward. Every expected signature of cometary activity appears. The astronomical community responds with relief and excitement. Relief because Borisov's behavior fits established categories, requires no exotic explanations, demonstrates that interstellar comets can be comprehensible. Excitement because this comprehensibility permits detailed study. An active comet observed over months provides vastly more data than Oumuamua's brief, enigmatic passage. Telescopes worldwide coordinate observation campaigns. Spectroscopy monitors gas production rates as Borisov approaches perihelion. Photometry tracks brightness changes and coma evolution. Imaging documents the tail's structure and dust distribution. The orbit brings Borisov to perihelion, closest approach to the Sun, on December 8, 2019, at a distance of 2.0 astronomical units. This places it between the orbits of Mars and the asteroid belt, far enough to prevent the violent sublimation and fragmentation that affects sun-grazing comets, close enough for solar heating to drive robust outgassing. The comet brightens steadily as it approaches. Following the relationship between distance and brightness established by thousands of solar system comets, The gas production rate increases predictably with solar flux. The coma expands. The tail lengthens. Every measurement confirms normalcy. Borisov acts exactly as solar system comets act under equivalent conditions. This normalcy itself carries significance. It suggests that comet formation processes, the condensation of ices and dust in the outer regions of protoplanetary disks, produces similar results across different stellar systems. The physics governing planet formation around the Sun also governs planet formation around Borisov's unknown parent star. Spectroscopic analysis identifies familiar molecules: sodium, C2, NH2, water vapor, the standard suite of cometary volatiles. The relative abundances fall within the range observed in solar system comets. No exotic chemistry, no unexpected compounds requiring explanation. Dust grain analysis, performed through polarimetry and thermal emission modeling, indicates particles similar in size and composition to solar system cometary dust, silicates, probably with organic mantles. Size distribution peaking around a few micrometers, typical. The nucleus itself remains unresolved, too small, too distant, too shrouded in its coma for direct imaging. But estimates derived from the comet's absolute magnitude and assumed albedo suggest a diameter between 0.4 and 1.0 kilometers. Again, ordinary. Many solar system comets fall within this size range. Researchers publish comparison papers contrasting Borisov with Oumuamua. The differences prove stark. Where Oumuamua appeared inert, Borisov outgasses vigorously. Where Oumuamua's shape defied easy interpretation, Borisov's morphology matches standard cometary structure. Where Oumuamua left fundamental questions unanswered, Borisov provides reassuring confirmation of existing models. The media covers the discovery. Though with less intensity than Oumuamua received, interstellar visitors have lost their novelty. The second occurrence confirms pattern rather than establishing precedent. And patterns, however interesting scientifically, generate less public fascination than mysteries. But within the astronomical community, Borisov represents a triumph. Proof that the first interstellar object's strangeness derived from Oumuamua's individual properties, not from interstellar origin itself. Proof that the galaxy contains comets fundamentally similar to our own. That the Sun's planetary system does not occupy a unique corner of cosmic chemistry. Observations continue through early 2020 as Borisov recedes from the Sun. The outgassing gradually diminishes. The coma fades. The tail shortens. By March, the comet has dropped below the detection threshold of most telescopes. Unlike Oumuamua's abrupt disappearance, Borisov's fade follows the predictable decline of a departing comet. No mysteries, no anomalies requiring years of debate. The data archives fill with spectra, images, photometric measurements. Papers analyze the composition, compare Borisov to solar system analogs, discuss implications for planet formation in other stellar systems. The consensus emerges smoothly. Borisov is a normal comet from an abnormal source. Its interstellar origin makes it scientifically valuable, but its properties suggest formation processes identical to those that built the Oort cloud, the Kuiper belt. The scattered disk populations of the Sun's domain only took millions of years to arrive from another star, and it behaved exactly as expected. And that ordinariness itself qualified as profound. The relief in the literature, unstated but palpable, reflects the strain that Oumuamua imposed on astronomical interpretation. 2 years of debate over acceleration mechanisms, shape, composition, origin. 2 years of uncertainty, of incomplete data, of questions without answers. Borisov resolved none of Oumuamua's mysteries, but it demonstrated that interstellar objects need not be mysterious, that comprehensibility remained possible, that the universe, for all its vastness and strangeness, sometimes offers straightforward examples matching theoretical predictions. This reassurance carried value. Science progresses through anomalies, observations that challenge models, that require new physics, that push understanding forward. But science also requires confirmation, validation, demonstration that existing models work in new contexts. Borisov provided that validation. The photographs show a fuzzy greenish blob, the coma's fluorescent glow, with a faint tail streaming away, visually indistinguishable from any of thousands of solar system comets imaged across decades of observation. But spectroscopic redshift measurements confirm the hyperbolic trajectory. Velocity relative to the solar system's barycenter exceeds escape speed. Borisov arrived from interstellar space, is departing to interstellar space, will never return. A visitor that looked familiar, that acted familiar, that fit. Except for the cyanide. Cyanogen, CN, a molecule consisting of one carbon atom bonded to one nitrogen atom, fluoresces in the violet portion of the visible spectrum when excited by solar ultraviolet radiation. Nearly all comets produce detectable CN emission. The molecule forms through photodissociation of larger parent molecules, likely HCN, hydrogen cyanide, sublimating from the nucleus. The amount of CN emission relative to other molecular species serves as a compositional diagnostic. Astronomers compare CN production rates to C2 production rates, dicarbon molecules also common in cometary comae. The ratio CN/C2 provides information about the relative abundances of carbon-bearing and nitrogen-bearing ices in the nucleus. Solar system comets show CN/C2 ratios typically ranging from 0.5 to 2.5. The value varies among individual comets, reflecting differences in formation location or subsequent processing, but remains within this observed range for the vast majority of measured cases. 2. I/Borisov's CN/C 2 ratio measures approximately 0.2 to 0.4, significantly below the typical solar system range. The measurement appears robust. Multiple independent spectroscopic observations from different telescopes yield consistent results. The uncertainty bars overlap the lower end of the solar system distribution, but place Borisov's central value distinctly depleted in CN relative to C2. This depletion suggests Borisov's nucleus contains less nitrogen-bearing ice relative to carbon-bearing ice compared to typical solar system comets, or alternatively, that the nitrogen exists in chemical forms less readily photodissociated into CN radicals, or that some aspect of Borisov's thermal history affected nitrogen retention differently than carbon retention. The interpretation requires understanding where comets form relative to their parent stars. In our solar system, comets originate primarily beyond the orbit of Neptune, in regions where temperatures permitted water-ice condensation, along with more volatile ices like CO2, CH4, and nitrogen compounds. The exact condensation sequence depends on local temperature and pressure. Nitrogen, with its low condensation temperature, incorporates into cometary nuclei only in the coldest regions or in chemical forms that trap it at higher temperatures. Ammonia, HCN. Organic nitriles. If Borisov formed in a region of its parent disk that was slightly warmer than the region where solar system comets formed, nitrogen depletion might result. The nitrogen remained gaseous while carbon-bearing molecules condensed. Or if the parent star's luminosity evolution differed from the Sun's, perhaps a more rapid increase in brightness during the pre-main sequence phase, the protoplanetary disk might have experienced thermal processing that preferentially removed nitrogen while retaining carbon. Or Borisov might represent a compositional subclass, rare but not absent in our own system, a depleted nitrogen comet that formed under specific local conditions, then was ejected before we could sample that population extensively. The uncertainty spans multiple branches of planetary science: protoplanetary disk chemistry, stellar evolution, ice condensation thermodynamics, comet formation mechanisms. From a single ratio, Cn/C2 approximately equal to 0. 3. Flows a cascade of possible implications, each requiring knowledge of processes operating billions of years ago around an unknown star. Researchers investigating Borisov's composition also measure isotopic ratios where possible. The ratio of deuterium to hydrogen in water vapor provides insight into formation temperature, Borisov's DH ratio, though difficult to measure due to the comet's faintness, appears consistent with solar system values within measurement uncertainties. This suggests similar thermal conditions during ice formation, arguing against extreme environmental differences between Borisov's birthplace and the Sun's protoplanetary disk. Yet the Cn depletion persists. Confirmed. Anomalous relative to typical solar system comets. Not wildly anomalous, not inexplicable, simply different. Shifted toward one end of the composition distribution, perhaps slightly beyond the observed range, indicating formation under conditions subtly unlike those that produced the Oort cloud population. A glitch in the expected chemistry. The molecular emission ratios, logged in spectroscopic databases, exist as numbers, wavelength, intensity, uncertainty. The Cn band at 388 nanometers shows integrated flux of x ergs per second per square centimeter. The C2 band at 517 nanometers shows integrated flux of y. The ratio xy equals 0.3 plus or minus 0.1. From these numbers, astronomers infer properties of ice that condensed around another star 4.5 billion years ago, that survived ejection into interstellar space, that endured millions of years at temperatures barely above absolute zero, that approached the Sun in 2019 and began sublimating, releasing molecules trapped since the epoch of planet formation. Those molecules fluoresce. Telescopes detect the fluorescence. Spectrographs disperse the light into constituent wavelengths, CCDs measure intensities, computers calculate ratios, and the ratio comes out slightly wrong. Not dramatically, not impossibly, just shifted, offset from expectation by amounts that exceed measurement uncertainty but fall within plausible physical scenarios. The kind of anomaly that invites investigation but doesn't demand revolutionary explanation. Papers discuss the Cn depletion in sections titled Implications for Formation Environment or Comparison with Solar System Comets. The discussion acknowledges the anomaly, proposes possible explanations, notes that additional observations of future interstellar comets would help constrain compositional diversity. The tone remains measured, scientific, appropriately uncertain given limited data. No one claims profound mystery. No headlines proclaim alien comet chemistry baffles scientists. Because Borisov doesn't baffle, it simply exhibits composition slightly outside the familiar range, requiring extension of models rather than abandonment of frameworks. Only took 4.5 billion years to form, and millions of years to arrive. And we measured its molecular emission ratios to 10% precision, and they deviated from typical values by amounts barely exceeding uncertainty bars. The comet continues its recession, now beyond Saturn's orbit, fading, inert, its volatiles exhausted, its nucleus returned to the frozen silence of deep space. The Cn molecules emitted during perihelion passage have dispersed into the solar wind, ionized, incorporated into the interplanetary medium. The photons they emitted during fluorescence traveled at light speed to Earth. Struck CCDs got recorded as digital values, and now exist only as archived data. The anomalous ratio persists in those archives, available for comparison when the third interstellar comet is discovered, or the fourth, or the 50th. Perhaps eventually a pattern will emerge. Perhaps Borisov represents the typical interstellar composition, and solar system comets are the anomalous population, enriched in nitrogen through some quirk of the Sun's formation environment. Or perhaps each stellar system produces comets with unique compositional signatures, fingerprints of their individual formation histories, or perhaps the scatter in CN/C2 ratios, both within the solar system and among interstellar visitors, simply reflects the inherent diversity of planet formation. The local variations in temperature and pressure that make each comet a unique sample of ancient chemistry. The universe offers data, interpretation remains human work, and Borisov's data shows CN depletion, confirmed, archived, awaiting context. The glitch in the expected chemistry persists, quiet, unresolved. Light scatters from dust grains through processes determined by grain size, shape, and refractive index. When unpolarized light, such as sunlight, strikes a small particle, the scattered light becomes partially polarized, with the degree of polarization depending on the scattering angle and particle properties. Astronomers measure this polarization using instruments that separate light into perpendicular polarization states. The percentage of polarization and its variation with observation geometry provide diagnostic information about the dust grain's physical characteristics. 4. Cometary dust. Polarimetry reveals grain sizes typically in the range of 1 to 10 micrometers, comparable to wavelengths of visible light. The regime where Mie scattering theory governs light interaction, smaller grains produce different polarization signatures than larger grains. Fluffy. Fractal aggregates scatter differently than compact, solid particles. Multiple observatories performed polarimetric observations of 2I/Borisov during its 2019 to 2020 apparition. The measurements, conducted across multiple wavelengths and observation geometries, reveal polarization properties distinctly different from typical solar system comets. Borisov's dust shows lower polarization at equivalent scattering angles compared to solar system cometary dust. This lower polarization indicates larger average grain size, particles measuring tens of micrometers rather than the few micrometers typical of solar system comets. Larger grains imply different formation or processing history. In protoplanetary disks, dust grain growth occurs through collisional aggregation. Particles stick together, building larger particles. The size distribution reached at any location depends on local density, turbulence, time available for growth, and the efficiency of sticking collisions. If Borisov's dust grains measure larger than solar system cometary dust, this suggests either more efficient grain growth in its formation region, or longer time available for growth, or less subsequent fragmentation during the comet's history. The polarimetric data also suggests Borisov's grains are more pristine, less processed by radiation, less altered by thermal cycling or impact shock than typical solar system cometary dust. Pristine grains retain more of their original structure from the protoplanetary disk. Processed grains show evidence of modification, amorphization of crystalline structures, compaction of fluffy aggregates, chemical alteration through radiation damage. Interstellar space, paradoxically, provides gentler conditions than the inner solar system. Temperatures hover barely above absolute zero. Radiation levels remain low compared to solar proximity. Impact rates from other particles drop essentially to zero in the vastness between stars. A comet ejected into interstellar space 4 billion years ago has spent those 4 billion years in cold storage, preserved against the processes that would alter it within a planetary system. No close passages to warm suns, no gravitational perturbations sending it sunward, no impact bombardment from debris populations, just silence. Cold, minimal radiation, perfect preservation conditions. Until Borisov entered the sun's influence, approached to 2 astronomical units, and began sublimating dust that had remained essentially frozen since its formation epoch. That dust, released into the coma, scatters sunlight with polarization properties indicating large, pristine grains. The solar system's comets, by contrast, have experienced multiple thermal cycles for those in short-period orbits, or at minimum, the initial passage that placed them in the Oort cloud, a passage involving close planetary encounters, gravitational scattering, possible collisional disruption. Even long-period comets making their first inner-system approach have spent billions of years in the Oort cloud, subjected to cosmic ray bombardment, galactic tide perturbations, occasional distant stellar passages. Processing accumulates. Grains fragment under radiation damage. Thermal cycling induces cracking. Impact gardening mixes surface and interior materials. Borisov, ejected early and preserved in interstellar isolation, escaped much of this processing. The polarimetric measurements thus provide glimpses of primordial dust, grains that condensed in another star's protoplanetary disk and survived essentially unmodified across billions of years. This interpretation, published in papers analyzing Borisov's polarimetry, carries implications for understanding dust evolution in planetary systems. It suggests that the dust properties observed in solar system comets reflect not only initial formation conditions, but also billions of years of subsequent modification. Separating initial conditions from processing effects requires comparison populations. Borisov provides one data point for that comparison. Future interstellar comets will provide more, but the sample size remains profoundly limited. 2 interstellar objects confirmed as of early 2025, one asteroid-like, Oumuamua, one comet-like, Borisov. Both observed incompletely, both faded before all desired measurements could be completed. From this sparse sampling, astronomers attempt to infer properties of the galaxy's general interstellar object population. Billions of rogue comets and asteroids presumably drift in interstellar space, ejected from planetary systems across cosmic history. Detection bias favors the largest, brightest examples passing closest to the Sun. Borisov's dust grains, larger, more pristine than typical solar system examples, might represent normal primordial dust, or might represent unusual formation conditions, or might reflect selection effects, where only comets that survived interstellar transport without fragmenting can be detected upon entering stellar systems. The uncertainty persists across multiple interpretive layers, but the measurement itself stands robust. Borisov's dust polarizes light less than solar system cometary dust at equivalent geometries, consistent with larger grain sizes and more pristine structure. The data exists in tables: wavelength, scattering angle, polarization percentage, uncertainty. Numbers derived from photons scattered by micrometer-scale particles that formed around an unknown star, traveled unknown distances, and happened to pass close enough to Earth for detection, only took billions of years to form and preserve, and we measured the polarization of their scattered light to within a few percent, and the measurement revealed properties subtly different from familiar examples. The grains themselves have dispersed, swept outward by radiation pressure. They join the interstellar medium, individually untrackable, destined to drift for millions more years until captured by another star's gravity or destroyed through collision with interstellar gas atoms. The polarization data remains. A signature of primordial dust. A glimpse of conditions in another stellar system's planet-forming disk. A measurement that fits within physical understanding while extending the observed range of cometary dust properties. A glitch in the expected grain size distribution. The universe permitted measurement of the glitch, then dispersed the evidence, leaving only archived photon counts as testimony. The telescope moves to its next target. The archive grows, and somewhere between stars, grains of ancient dust continue their journey, unpolarized, unobserved. Automated sky surveys operate continuously, imaging the same fields repeatedly, searching for change. A star that brightens, an asteroid that moves, a supernova that appears where no star existed in previous exposures. The software pipeline processes thousands of images per night. Subtract the reference image from the new image. Identify pixels showing significant flux change. Classify the change. Cosmic ray, satellite trail, variable star, transient, artifact. The classification algorithms achieve high accuracy through training on millions of examples. Machine learning models learn to distinguish real astrophysical events from instrumental effects. Statistical fluctuations, processing errors, but accuracy below 100% means errors accumulate. With millions of detections per year, even 99.9% accuracy generates thousands of false classifications, some false positives. Algorithms flag instrumental artifacts as real transients, triggering follow-up observations that reveal nothing. Some false negatives. Algorithms dismiss real transients as artifacts, consigning genuine discoveries to the rejected data stream. The balance between these error types represents engineering compromise, too sensitive, and the system drowns in false alarms, too conservative, and rare events escape detection. Survey operators tune classification thresholds based on science priorities. A survey hunting for rare supernovae types accepts higher false positive rates to avoid missing genuine examples. A survey cataloging variable stars requires higher confidence thresholds to maintain catalog purity. But tuning for one science case degrades performance on others. And some events exist at the boundary, neither clearly real nor clearly artifactual, exhibiting characteristics of both categories simultaneously. An automated survey in Chile detects a brightening event on March 15, 2023. The alert system flags it as possible supernova, point source, not present in reference images, brightness consistent with distant stellar explosion, blue color matching hot ejecta. Follow-up spectroscopy gets scheduled. Before the observation occurs, the object brightens further. The magnitude increase exceeds typical supernova rise rates. The color shifts redder. Then the object fades. 2 days after detection, it has dimmed below the survey's detection threshold. This rapid evolution, rise, peak, fade over 72 hours, falls outside supernova parameter space. Supernovae evolve over weeks to months, but the photometry showed genuine point source morphology, not the extended shape characteristic of solar system objects. The spectroscopic observation captures only noise. The object has faded too much. The spectrum contains insufficient signal for classification. Subsequent investigation reveals the brightening coincided with a subtle drift in the telescope's tracking system. Over the 3-night window, the pointing accuracy degraded by approximately 1 arcsecond, minimal, below typical seeing disk sizes, insufficient to degrade image quality noticeably, but sufficient to slightly shift the position of a faint background star relative to the reference image. The shift created artificial flux variation when the subtraction algorithm compared images. The variation mimicked a real transient. The event gets reclassified. Instrumental artifact due to tracking error. Except the tracking error alone cannot fully explain the observed brightness changes. The magnitude of the variation exceeds what pointing drift should produce. And the color change, blue to red over 2 days, remains unexplained by simple positional offset. A residual mystery persists. Something happened in that field on those nights. Whether purely instrumental or partially astrophysical cannot be determined from available data. The follow-up opportunity has passed. The field continues being surveyed, but the transient, if real, has faded or moved or ended. The specific combination of conditions that produce the detection cannot be reproduced. The event joins a catalog of unconfirmed transients. Thousands of similar cases exist across survey archives. Detections that triggered alerts, then proved ambiguous upon investigation. Neither definitively real nor definitively false. Some fraction represent genuine astrophysical events that happen to coincide with instrumental issues, creating confusion that obscured their true nature. Others represent purely instrumental artifacts that mimicked astrophysical signatures through coincidence. Distinguishing these categories retrospectively, using only archival data, often proves impossible. The photometric data exists: Julian date, magnitude, filter, uncertainty, 3 detections over 3 nights showing a brightening curve that resembles dozens of known transient types while matching none perfectly. Also exists telemetry data showing minor tracking drift during the same period, sufficient to explain some but not all observed effects. The interpretation fractures. Was it real? Was it artifact? Was it both? A real background event amplified by coincidental instrumental issue? Only took billions of years for the light to arrive, and 72 hours to brighten and fade, and we captured 3 data points before it vanished, and those 3 points remain forever ambiguous. The irony settles into the archive alongside the data itself. Survey operations continue. The telescope images the same field again, monthly, accumulating reference frames, searching for new transients. The field contains nothing unusual. Thousands of faint galaxies, scattered stars, a quasar near the detection limit. Nothing that would obviously produce a 3-day transient brightening event. But absence of obvious explanation does not constitute proof of artifact. The catalog entry remains flagged. Probable instrumental artifact. Classification uncertain. The photometry remains available for analysis. Future researchers investigating rare transient types might revisit the event, armed with improved instrumental models or new understanding of fast astronomical transients, or the event will rest forever in the catalog's ambiguous category, one of thousands. A data point that exists but resists interpretation, the glitch that might have been real, the detection that shouldn't have triggered alerts but did, the boundary case that exposes the limitation of automated classification, the irreducible uncertainty when observation and instrument interact in complex ways, somewhere in the archive. Pixels hold elevated counts from those 3 nights in March 2023. The counts are real. Photons genuinely arrived at the detector. Liberated electrons in the CCD wells got converted to digital values, transmitted to storage. Whether those photons originated from an astrophysical source, or from scattering within the instrument, or from electronic noise in the readout chain, cannot be determined with available evidence. The universe does not label its signals, does not distinguish for observers' benefit between meaningful and meaningless variation, simply provides photons, and leaves interpretation to minds evolved for pattern recognition. Now attempting pattern recognition in parameter spaces alien to terrestrial experience. Sometimes those minds succeed. The pattern matches known categories. Classification proceeds confidently. Sometimes they fail. The pattern resists categorization. Uncertainty persists. And sometimes, perhaps the most unsettling case, they partially succeed. The pattern almost matches, fits most criteria but violates others, suggests classification while withholding definitive evidence. The March 2023 event occupies this third category. Almost certainly artifact, probably not astrophysical. But the almost and probably cannot be elevated to certainty without additional data that will never arrive. The glitch in the photometric pipeline, the ghost in the detection system, the event that existed for 72 hours, then vanished, leaving only ambiguity. On July 2014, a radio telescope in Puerto Rico detects a millisecond duration burst of radio emission. The signal appears in data recorded as part of a pulsar survey, a long-term program monitoring known pulsars and searching for new examples. But this signal originates from wrong sky coordinates, not from any catalogued pulsar, not from any known source. The burst shows dispersion. Different radio frequencies arrive at slightly different times, with lower frequencies delayed relative to higher frequencies. This dispersion signature results from the signal passing through ionized plasma. The amount of dispersion indicates the total electron density integrated along the line of sight. For the 2014 burst, the dispersion measure exceeds any plausible value for Milky Way plasma. The electrons contributing to the delay must exist in intergalactic space, implying cosmological distance. The source lies billions of light-years away. A millisecond burst from a source billions of light-years distant requires extraordinary energy output. The calculation depends on assumed distance and emission geometry, but for reasonable assumptions, the burst luminosity equals the Sun's total energy output over 10,000 years, compressed into 1 millisecond. What astrophysical process generates such events? The question remains partially unanswered. The leading model invokes magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's field. Magnetic reconnection events, or crustal fractures in these extreme environments, might produce coherent radio emission of sufficient brightness. But magnetars exist in our galaxy. The 2014 burst, based on its dispersion, originated far beyond the Milky Way. So, either distant galaxies contain magnetars, and occasionally we detect their giant flares, or some other mechanism entirely produces these fast radio bursts, the designation given to this phenomenon. More bursts are discovered. Some show repetition, multiple bursts from the same sky position over weeks or months. Others appear once and never again. The repeating sources permit localization to specific host galaxies. The one-off events resist precise localization, their sky positions uncertain to arc-minute scales. The repeating FRB sources revolutionize the field. If a source repeats, telescopes can monitor it, waiting for the next burst. This permits multi-wavelength observation campaigns impossible for one-off events. In December 2016, a repeating FRB gets localized to a dwarf galaxy approximately 3 billion light-years distant. The galaxy appears otherwise unremarkable, low mass, low metallicity, actively forming stars. No obvious feature distinguishes it from millions of similar galaxies. Except one region of this galaxy occasionally emits millisecond radio bursts visible across cosmological distances. The bursts show no obvious periodicity, no predictable pattern. They simply occur sporadically, with intervals ranging from minutes to months. This sporadic timing initially led to dismissal of many FRB detections as instrumental artifacts. Radio telescopes operate in environments contaminated by human-generated radio signals. Satellites, aircraft, ground-based transmitters, electrical equipment, all produce radio emission that can mimic astronomical sources. Sophisticated filtering algorithms attempt to distinguish astrophysical from terrestrial signals. They examine dispersion. Terrestrial signals show minimal dispersion. Polarization. Terrestrial signals often show different polarization properties. And temporal structure. Terrestrial interference often shows characteristic timing patterns. But edge cases exist. Terrestrial signals that happen to show dispersion-like effects due to propagation through Earth's ionosphere. Timing glitches that mimic burst structure. Polarization states that coincidentally resemble astrophysical predictions. The early FRB detections faced skepticism precisely because they appeared too strange. Millisecond bursts from cosmological distances, with no obvious progenitor model, detected primarily by one telescope using specific analysis methods. Only after multiple independent observatories confirmed FRB detections, using different instruments and analysis pipelines, did the astronomical community accept the phenomenon as astrophysical rather than artifactual. Even then, some individual detections remain disputed. A 2018 burst showed characteristics suggesting terrestrial origin, dispersion measure slightly lower than expected for the claimed distance, arrival time coinciding with local radar operations. But the detection pipeline flagged it as astrophysical. The classification got disputed in follow-up papers. The burst joins the ambiguous category, probably terrestrial, possibly astrophysical, insufficient data for certainty. Meanwhile, confirmed FRBs accumulate in catalogs. As of 2025, hundreds are known. The detection rate increases as more radio telescopes implement FRB search capabilities. Some bursts show accompanying X-ray emission, detected by space-based observatories monitoring the same sky region. This multi-wavelength detection confirms the magnetar model for at least some FRBs. Magnetar flares produce both radio and X-ray emission, but many FRBs show no detected X-ray counterpart. Either the X-ray emission is too faint, or these bursts arise from a different mechanism, or observational coverage was insufficient. The glitch in the radio telescope data, the millisecond spike that shouldn't exist, that mimics instrumental effects, that required years to confirm as astrophysical, has become routine, expected, catalogued. What was anomaly is now phenomenon, a new class of astronomical transient, recognized, characterized, modeled, but individual detections still sometimes fall into ambiguity. The borderline cases where signal resembles both astrophysical burst and terrestrial interference, where classification algorithms assign 50% probability to each interpretation, where human judgment weighs evidence and finds it balanced. These ambiguous cases accumulate alongside confirmed detections. They exist in a liminal state, not proven false, not confirmed real, awaiting additional evidence that may never materialize because the events are transient, non-repeating. Gone before follow-up observation could be arranged. Only took 13 billion years for the light travel time, and 1 millisecond for the burst duration, and decades of radio telescope development to achieve detection sensitivity. And sometimes we still cannot confidently distinguish signal from noise. The irony compounds. The universe generates the brightest radio events observable across cosmological distances, and human instruments barely detect them above local interference levels. The catalogs grow, confirmed FRBs, probable FRBs, possible FRBs, disputed detections. Each category contains its population, its uncertainty ranges, its debates, and in the radio telescope data streams, more candidate bursts appear nightly. Software flags them. Astronomers examine them. Classification proceeds. Most resolve clearly, real or artifact. Some resist resolution. The edge cases. The glitches in the detection pipeline that might be glitches in the cosmos. The millisecond burst that existed, or didn't, depending on interpretation. The signal from everywhere and nowhere. A telescope's optical system creates artifacts inherent to its design. Bright stars generate diffraction spikes, the characteristic cross-shaped pattern extending from point sources. Produced by light diffracting around the secondary mirror's support struts. The number, orientation, and extent of these spikes depend on the specific mirror support geometry. Hubble Space Telescope images show four-pointed diffraction spikes, reflecting its four-strut secondary mirror support. The James Webb Space Telescope, with its six-strut hexagonal mirror configuration, produces six-pointed spikes plus additional fainter features from the hexagonal segment gaps. These spikes contain no astronomical information. They represent pure optical artifact, light redistributed by diffraction from its original point source location into extended features. Yet they possess aesthetic quality. The spikes add visual structure to otherwise empty fields. Photographers sometimes enhance them during image processing, strengthening the effect for artistic impact. Ghost reflections occur when light bounces between optical surfaces within the telescope. Lens elements, filters, detector windows. The ghost appears as a faint, out-of-focus replica of a bright source, often colored differently due to wavelength-dependent reflectance. Careful optical design minimizes ghosting, but cannot eliminate it entirely when imaging very bright objects. A particularly bright star might generate multiple ghosts, each from reflection between different surface pairs. These ghosts form geometric patterns predictable from the optical layout. Software can model and subtract them, though imperfectly, but sometimes a ghost coincides with the position of a faint, real object, the subtraction algorithm. Attempting to remove the ghost also removes the real source, or incompletely subtracts the ghost, leaving residual flux that gets interpreted as a faint, extended source. Cosmic rays strike CCDs as previously discussed, leaving tracks and spots, but sufficiently energetic particles can cascade through the detector substrate, creating complex patterns that resist simple identification. A cosmic ray hitting at shallow angle might create a track spanning dozens of pixels, potentially mimicking an asteroid trail or satellite passage. Advanced cosmic ray rejection algorithms compare images taken at different times or with different dither positions. A real astronomical object appears consistently across exposures. A cosmic ray hit appears randomly in single frames, except for the rare case where cosmic ray hits coincidentally occur in the same detector region across multiple exposures. Statistically unlikely, but not impossible given millions of exposures. The algorithm sees consistency, interprets it as real source, accepts the artifact into the final processed image. These optical and detector artifacts create a visual language familiar to anyone who works extensively with telescope data. The eye learns to recognize diffraction spikes instantly, to mentally filter them from consideration when examining images. The mind develops intuition for ghost patterns, for cosmic ray morphologies, for all the ways instruments inscribe their presence onto images of the cosmos. But this familiarity creates its own hazard. Pattern recognition tuned to ignore artifacts might overlook genuine objects that happen to resemble instrumental signatures. An extended source with elongated morphology might get dismissed as satellite trail. A point source that appears in only one filter might get rejected as cosmic ray hit. A faint streak might get classified as diffraction artifact when it actually represents a distant asteroid or Kuiper belt object. The classification proceeds based on probability. Most streaks are artifacts. Most single-filter detections are cosmic rays. Most ghost-like features are ghosts. But most differs from all. And in the gap between these concepts rests the possibility of misclassification. Real objects rejected as fake, astronomical discoveries consigned to the artifact catalog. How often this occurs remains unknown. The objects get rejected precisely because they resemble artifacts. They don't receive follow-up observation. They disappear into the data stream's noise floor. Occasionally, retrospective analysis recovers them. A researcher investigating a different question examines archival images and notices a cosmic ray that appears in the same location across multiple exposures separated by months. The consistency suggests real source. Further investigation confirms a genuine trans-Neptunian object, moving slowly enough that its motion barely registers over short time scales. Misclassified as artifact because it appeared in single exposures of each multi-exposure set. The object gets reclassified. The discovery gets published, though credited to archival analysis rather than initial detection. How many remain unrecovered? How many detections, flagged as probable artifact, actually represent rare astronomical phenomena? The question has no answer. The objects, if they exist, remain invisible within the much larger population of confirmed artifacts, but statistical arguments suggest some must exist. With millions of detections flagged as artifacts, even a false rejection rate of 0.01% implies hundreds of genuine objects misclassified. They rest in the archives, labeled cosmic ray or ghost or diffraction artifact or processing error. Available for re-examination, awaiting the specific query that might reveal their true nature. Meanwhile, the artifacts themselves, the genuine instrumental effects, create images of surprising beauty. A bright star's diffraction pattern, spreading symmetric spikes across the field, an internal reflection creating a rainbow-hued ghost, a cosmic ray cascade illuminating the detector's crystalline structure through its charge deposition pattern. These are the telescope dreaming in artifact, the instrument inscribing its own signature onto observations, creating patterns that reflect optical design rather than cosmic reality, yet possessing their own aesthetic. Astrophotographers sometimes celebrate these artifacts. Images get selected for public release partly based on dramatic diffraction spikes. The artifacts enhance rather than detract from visual impact, but for scientific analysis, they represent contamination, signal to be removed, patterns to be suppressed in pursuit of the pure astronomical information beneath. The tension between aesthetic and scientific value persists across the field. An image can be beautiful because of artifacts while being scientifically degraded by them. Conversely, scientifically optimal images, heavily processed, artifact removed, noise suppressed, often lack visual drama. Public outreach images typically balance these considerations. Starting from scientifically processed data, graphic designers reintroduce some artifact elements for visual interest. Diffraction spikes get enhanced, color saturation gets increased. The result? Images that communicate scientific content while maintaining aesthetic appeal. But this processing creates its own category of glitch, images that depict real objects using partially artificial rendering. The nebula exists, the colors are real, though shifted from actual wavelengths to visible range. The stars are genuine, but the specific shade of blue, the intensity of the diffraction spikes, the contrast levels, these reflect processing choices rather than raw photometric measurements. For public understanding, this introduces ambiguity. What parts of an astronomical image represent direct observation versus artistic interpretation? The question has no simple answer. Every image undergoes processing. Even raw images have been flat-fielded, bias subtracted, cosmic ray rejected. The glitch expands. Not just instrumental artifacts contaminating data, but the entire pipeline of observation, processing, and presentation, creating layers of transformation between cosmic reality and human perception. Photons depart a nebula 6,000 years ago. They cross interstellar space, maintaining their wavelength information, their polarization, their directional vector. They enter a telescope aperture, focus onto a detector, liberate electrons, get digitized. The resulting numbers get processed through dozens of algorithmic steps: calibration, artifact removal, noise reduction, combination with other exposures, color mapping, contrast adjustment. The final image, the picture a person sees, represents that ancient light filtered through all these transformations, faithful to the original in some senses, heavily modified in others. Where along this chain does the real image exist? In the raw detector counts, uncalibrated, uncorrected. In the scientifically processed data, artifacts removed, calibrated to physical units. In the public release version, color enhanced, visually optimized. Each serves different purposes. Each constitutes valid representation of different aspects of the observation. But each also contains its own category of glitch. The raw data, contaminated by instrumental artifacts. The scientific version, degraded by imperfect correction algorithms. The public version, modified by aesthetic choices. Only took 6,000 years for the light to arrive, and microseconds to detect, and hours to process. And the result is an image simultaneously faithful and artificial, real and constructed, observation and interpretation merged inseparably. The telescopes continue imaging, the artifacts continue appearing, the processing pipelines continue their work, and in the archives accumulate millions of images, each containing some mixture of cosmic reality and instrumental signature, each representing successful detection of distant light despite the imperfections inherent in the detection process. The universe provides photons. Telescopes provide artifacts. Processing provides interpretation. Together they create the visual record of the cosmos, glitched, imperfect, but sufficient for understanding to accumulate across generations of observation. The diffraction spikes spread their geometric patterns across fields of stars. The ghosts hover faintly near bright sources. The cosmic ray tracks streak through exposures, and beneath, around. Intermingled with these artifacts, galaxies, nebulae, stars, planets, the actual subjects of observation, real, distant, waiting patiently to be distinguished from the instrumental effects that accompany their detection. The eye learns discernment, the mind develops filters, science proceeds, and occasionally, very occasionally, something that appeared to be artifact turns out to be real. A glitch in the glitch, a pattern within the noise that actually matters. The archive preserves both, without distinction, awaiting recognition. In 2007, researchers at Oxford University launched Galaxy Zoo, inviting public volunteers to classify galaxy morphologies in images from the Sloan Digital Sky Survey. The task: examine galaxy images, determine whether they appear spiral or elliptical. Note features like bars, merger signatures, irregularities. The project receives overwhelming response. Within the first year, more than 100,000 volunteers classify millions of galaxies. The rate of classification far exceeds what professional astronomers could accomplish, but more significantly, the volunteers find anomalies that automated algorithms miss. Algorithms trained to classify galaxies use machine learning on large datasets. They achieve high accuracy for typical cases: clear spiral, obvious elliptical, standard irregular. But edge cases, unusual morphologies, rare types, these often get misclassified or flagged as uncertain. Human pattern recognition. Shaped by evolution for different purposes but remarkably flexible, excels at precisely these edge cases. The brain notices something strange, even when it cannot articulate what specifically appears unusual. A volunteer examining galaxy images notices an object that doesn't fit standard categories. Not spiral, not elliptical, not obviously irregular, instead, a bright green arc, roughly symmetric, with central compact source. The volunteer flags it as unusual. The image gets routed to professional astronomers for evaluation. Analysis reveals the object, designated Hanny's voorwerp, Dutch for Hanny's object, after the volunteer who discovered it, as a cloud of ionized gas illuminated by a quasar's radiation. The quasar itself has faded, but the light cone that ionized the gas cloud continues propagating outward, creating visible fluorescence in the gas. The discovery represents a rare catch, a light echo on galaxy-scale dimensions, revealing a quasar's past luminosity state. Automated classification algorithms, trained on typical galaxy morphologies, flagged Hanny's voorwerp as artifact or processing error. Its unusual green color from forbidden oxygen emission lines and peculiar geometry didn't match training categories. The algorithm's confidence values placed it below threshold for professional examination. A human eye saw it. A human mind recognized it as potentially interesting despite not understanding what it was. Human curiosity prompted the flag, and a rare astrophysical phenomenon got documented. This pattern repeats across citizen science projects. Volunteers find novae that automated transient searches miss. They identify variable stars with unusual light curves. They spot faint satellite trails indicating previously uncatalogued orbital debris. The human advantage rests not in superior processing speed. Algorithms examine millions of images far faster than any human could, but in flexibility. Human perception handles novelty better. Algorithms excel at recognizing trained categories. Humans notice deviations from expectation even when they cannot categorize them, in astronomical data streams. Most detections fall into known categories. The algorithm's efficiency handles the bulk processing, but the small fraction that doesn't fit, that exists at the boundary of established classification, these require human attention. Projects like Galaxy Zoo harness this by showing images to multiple volunteers. If several independently flag the same object as unusual, it receives professional examination. The redundancy filters individual error. One person might mistakenly flag a common galaxy as unusual, but multiple independent flags suggest genuine anomaly. This approach has discovered extremely rare galaxy morphologies representing merger types not previously documented, faint tidal streams from past galactic interactions, previously unknown planetary nebulae, misclassified by algorithms as distant galaxies, unusual variable stars with light curves suggesting new pulsation modes, gravitational lenses not detected by automated lens-finding algorithms. Each discovery existed in the data already. The photons had been collected. The images were stored. Automated pipelines had processed them. But classification failed. The algorithms, lacking context for novelty, imposed nearest available category or rejected as artifact. Human examination recovered the discoveries. How many remain unrecovered? How many images? Classified automatically. Contain objects that would be scientifically interesting if noticed, but rest unexamined in archives? The question has partial answer through statistics. Citizen science projects typically examine subsets of larger surveys. Galaxy Zoo analyzed approximately 1 million Sloan galaxies from a catalog of hundreds of millions. The examination uncovered several hundred unusual objects, rare morphologies, odd colors, unexpected features. Extrapolating suggests tens of thousands of similarly unusual objects exist in the unexamined portion of the survey. They remain invisible not because they're faint, they're bright enough for detection, but because no human eye has examined them individually. Automated classification will improve. Machine learning advances continuously. Future algorithms will detect novelty more flexibly, flag anomalies more sensitively, but more flexibly still differs from human cognition's fundamental approach to pattern recognition. Algorithms improve through training on larger data sets, better feature extraction, refined classification criteria. Humans notice things that seem wrong, interesting, odd, beautiful. The aesthetic response couples to pattern recognition in ways that algorithms don't naturally replicate. An astronomer browsing archival images for one purpose might notice something entirely unrelated that triggers curiosity. This tangential discovery mode, finding X while looking for Y, represents significant discovery pathway in science history. Algorithms don't browse. They execute specific searches, return results matching defined criteria. Serendipity requires flexibility in attention, in noticing peripheral details. Only took billions of years for galaxies to evolve their morphologies, and decades for telescopes to image them. And one volunteer examining the 19,367th image in their classification session noticed something green and weird that algorithms ignored. The human eye as final arbiter of anomaly. The irreplaceable pattern recognizer. Not because human vision exceeds instrumental capability, it doesn't, obviously, but because human cognition handles, I don't know what this is, but it seems important, better than current algorithmic approaches. The archives continue growing. Petabytes of astronomical images accumulate annually. The data volume far exceeds human examination capacity. Algorithms handle the bulk processing, extract standard measurements, catalog typical objects, measure established parameters, and occasionally, humans look, browse, notice, and find the green arc that shouldn't exist, the galaxy that spirals the wrong direction, the star that varies in a pattern never previously recorded. The glitches in the cosmic catalog, hiding in plain sight, waiting for the specific combination of human curiosity and attention that reveals them. Citizen science projects continue recruiting volunteers. The images continue their distribution to thousands of eyes worldwide. Classification proceeds, redundantly, inefficiently by algorithmic standards, but effectively at catching novelty. And in the intersection between algorithmic efficiency and human flexibility, discoveries accumulate. The things the telescopes saw but the computers missed. The patterns that required biological neural networks for recognition. The glitches that only humans noticed. An observation gets made, processed, analyzed, published, filed in the archive with classification, known phenomenon, understood process, consistent with models. Decades pass, theory advances. New physics gets discovered in particle accelerators, or predicted through cosmological simulations, or inferred from observations in other wavelengths. The advancement doesn't necessarily relate to the original observation. It addresses different questions, explores different domains. But sometimes the new theory carries implications for old data. A researcher, pursuing entirely separate investigation, recognizes that archival observations, perhaps flagged decades earlier as artifact or noise, might contain signatures of the newly understood process. The archive gets queried, old data gets retrieved, reprocessed using modern techniques, reanalyzed through the lens of current understanding, and occasionally, the reject pile yields discoveries. Examples accumulate across astronomical history. Pulsar signals detected in 1967 were initially dismissed as terrestrial interference, LGM for little green men, due to their artificial-seeming regularity. Only after recognizing neutron stars as plausible sources did the signals transition from rejected artifact to Nobel Prize-worthy discovery. X-ray observations from the 1970s showed variable sources whose rapid flickering exceeded theoretical limits for stellar mass objects. Initial reaction, instrumental error. The detectors couldn't actually be seeing brightness variations on millisecond timescales. Some electronic effect must be creating apparent fluctuations. Only after developing models of accretion onto neutron stars and black holes did the community recognize the variations as real, carrying information about matter behavior in extreme gravitational fields. Gamma-ray bursts, first detected by military satellites monitoring for nuclear weapons tests, were classified for years before astronomers recognized them as astrophysical. The satellite's data languished as classified information. When finally released and analyzed astronomically, the bursts revealed a population of the most energetic explosions in the universe, occurring billions of light-years away. Each case follows similar pattern. Observation precedes understanding. The data gets collected but cannot be properly interpreted within existing frameworks. Classification defaults to artifact or anomaly, or requires further investigation. Time passes. Understanding evolves. Context develops. Someone, often pursuing unrelated research, encounters the old data and recognizes it with new eyes. The reject pile gets revisited. The anomalies get reclassified. What was noise becomes signal. This pattern suggests that current archives contain observations whose significance remains unrecognized, data classified as artifact or unexplained, awaiting theoretical frameworks that will render it comprehensible. But which observations? What data? No method exists for identifying them ahead of time. If we could recognize them as important, they wouldn't rest in the reject pile. They exist there precisely because current understanding cannot accommodate them. They await future science. The waiting might span decades. Pulsar signals sat in archives for months before recognition. Gamma-ray burst data waited years. Some X-ray observations took a decade to transition from spurious to scientifically significant, and some observations might wait longer still. Data collected in 2025 might not achieve proper interpretation until 2045 or 2075 or beyond. When theoretical physics or computational methods or observational context finally provides the necessary framework, the archive serves as time capsule, not just preserving images and spectra, but preserving puzzles, questions frozen in digital storage, waiting for the moment when answers become possible. This preservation carries both hope and frustration. Hope, valuable data is not lost, remains available for future insight. Frustration. Current researchers cannot access that future insight, cannot distinguish the important but unrecognized from the genuinely spurious. Every rejected observation might be significant, or genuinely might be artifact. The two categories look identical until understanding advances enough to distinguish them. A survey conducted in 2003 detected 15 anomalous infrared sources, objects too bright at mid-infrared wavelengths relative to their optical brightness, showing unusual spectral energy distributions. Initial classification, probably artifact, perhaps scattered light from bright nearby sources, or electronic noise in the detector, or cosmic ray contamination creating false infrared excess. The observations got flagged, noted in papers as requiring confirmation, then largely forgotten as the survey moved to new targets and new science questions. In 2018, a researcher investigating high redshift galaxy formation queried the same survey archive, searching for distant dusty galaxies. Dusty galaxies emit primarily at infrared wavelengths, with relatively faint optical emission. Their spectral energy distributions show strong infrared excess. The search algorithm retrieved the 15 anomalous sources from 2003, re-examined with improved analysis techniques and better understanding of high redshift galaxy properties. 13 proved to be exactly that: distant dusty galaxies at redshifts between 2 and 4. Their light emitted when the universe was approximately 3 billion years old. The other two remain ambiguous, possibly artifacts, possibly unusual foreground objects. Insufficient data for definitive classification even with modern analysis. But the 13, dismissed as probable artifacts in 2003, became in 2018 valuable additions to catalogs of high redshift galaxies. The discovery dates are listed as 2018, when they were recognized, not 2003 when initially detected. The 15-year gap represents the time required for observational context and theoretical models to develop sufficiently for proper interpretation. Only took 13 billion years for the light to travel, and the observations sat in the reject pile for 15 years before anyone recognized what they were. The pattern might be common. Survey archives contain millions of flagged anomalies, most legitimately artifacts, some fraction representing real objects awaiting recognition. Distinguishing them requires either systematic re-examination of all flagged data using improved methods, serendipitous rediscovery when future searchers query archives for different purposes, development of new theories that predict specific observational signatures, prompting targeted archival searches. All three occur. Some research groups systematically mine archives, applying modern algorithms to old data. Others stumble upon discoveries while pursuing different questions. Theorists occasionally predict phenomena, then search archives for examples collected before the prediction. But the archive volume exceeds examination capacity. Most flagged anomalies will never receive detailed re-examination. They rest in digital storage, classified, catalogued, available but unvisited, somewhere in that vast collection. Observations that will someday be recognized as important. Data points that will contribute to Nobel Prize-winning discoveries. Measurements that contain signatures of physical processes not yet imagined. They exist now, indistinguishable from the much larger population of genuine artifacts, cosmic ray hits, instrumental glitches, processing errors. The glitches that aren't glitches, the artifacts that are actually real, the rejected data awaiting redemption. Time will sort them, eventually, perhaps, or they will rest forever in the archive's reject pile, their significance unrecognized, their information content unclaimed. The universe provided the signal. Human instruments detected it. Human understanding wasn't ready. And the photons, having traveled billions of years to reach detectors, got classified as noise and filed away, patient still, available still, waiting still, for theory to catch up to observation, for understanding to illuminate what currently appears dark, for the glitch to become the discovery. A charge-coupled device exposes for some duration, seconds, minutes, occasionally hours for faint targets. During this time, photons accumulate in pixel wells. The detector integrates arriving light, building signal, then exposure ends. Readout begins. The CCD transfers accumulated charge row by row to its readout register. The process requires time. Milliseconds to seconds depending on detector size and readout speed. During this readout interval, the detector cannot simultaneously collect new images. The universe continues during readout. Stars continue varying. Asteroids continue moving. Supernovae continue evolving. Transient events occur. But the detector, occupied with transferring data from previous exposure, misses these moments. They fall into the gap between exposures, the dead time. For most astronomical phenomena, dead time introduces negligible error. Stars vary on time scales of hours to days. Asteroids move predictably. Missing a few seconds between exposures loses no scientifically significant information. But for rapid transients, events lasting seconds or less, dead time matters critically. A gamma-ray burst might peak and fade during the gap between exposures. A stellar flare might rise and fall. A fast radio burst might occur when no telescope points at its source. The universe operates continuously. Human observation samples discretely. The gap between samples contains unobserved reality. This gap exists at multiple scales, between individual exposures, seconds of dead time, between observing runs, months when a telescope points elsewhere or waits for target to return to night sky, between survey passes, days or weeks before the same field gets re-imaged, and at the largest scale, between the era before telescopes and the era after. Millennia when events occurred unobserved, undocumented, lost to history except for those few bright enough for naked eye detection. A supernova explodes in a distant galaxy in the year 1823, bright enough for detection by telescopes of that era, but occurring in a region of sky not monitored regularly. No astronomer happens to point a telescope at that galaxy during the supernova's visible phase. The event occurs, peaks, fades, leaves no record in human knowledge. Evidence might persist. The supernova ejecta continues expanding. Modern observations might detect the remnant, a shell of hot gas, bright in X-rays, expanding at thousands of kilometers per second. Dating the remnant from expansion speed and current radius yields approximate explosion epoch, but the explosion itself, the optical transient that would have been visible for weeks, unobserved. It fell into the temporal gap between systematic sky monitoring. How many supernovae, how many novae, how many stellar outbursts occurred between when Galileo first pointed a telescope skyward in 1609 and when automated all-sky surveys began in the late 20th century? Thousands, certainly, tens of thousands, likely. All occurring unobserved because humanity's observational coverage remained sparse, many telescopes, but each monitoring tiny fractions of the sky, leaving vast areas unobserved. The gaps contracted slowly. Photographic surveys beginning in the late 1800s provided broader coverage. Automated surveys starting in the 1990s dramatically increased cadence and sky coverage, but gaps persist even now. The entire sky monitored every night? Impossible. Too much sky, too few telescopes. Survey strategy balances coverage against depth. observe large areas shallowly, detecting only bright events, or observe small areas deeply, detecting fainter events in limited regions. Either choice leaves gaps. Faint events in wide area surveys, any events in the unmonitored portions of deep surveys, and always the dead time between exposures, the readout gaps, the moments when detectors transfer data rather than collect it. For ground-based observatories, additional gaps from weather, clouds, daylight, atmospheric conditions. The sky exists continuously, but terrestrial observers access it intermittently. For space observatories, gaps from scheduling, many telescopes, limited time. Each target receives allocated minutes or hours. The rest of the sky goes unobserved during that period. The universe contains events perfectly suited to human detection capability, bright enough, occurring nearby enough, lasting long enough, that nonetheless escape detection because they occur during observational gaps. They happen in the stillness between exposures, in the readout time when the detector's attention turns inward to its own data management, in the interval when one observatory has finished observing and another has not yet begun, in the weather gap when clouds obscure the sky, in the scheduling gap when all telescopes point elsewhere. The events occur. Photons depart their sources, traveling at light speed toward Earth. They arrive, they strike atmosphere, or mirror, or empty space where no telescope waits, and their information content disperses, unrecorded. A gamma-ray burst in 2019 occurs while Swift Observatory downloads data from its previous observation. The burst location falls within Swift's field of view. The detector would have recorded it, but timing places the burst during dead time. 10 seconds of readout gap. The burst rises, peaks, fades during those 10 seconds. Other observatories, pointing different directions, miss it. By the time Swift completes readout and begins its next exposure, the burst has ended. Evidence of its occurrence appears in data from other satellites, a brief detection at lower sensitivity, insufficient for detailed characterization, enough to confirm that something occurred, not enough to measure its properties precisely. The burst joins catalogs as poorly constrained event, minimal data. Its redshift remains unknown, its energy output uncertain, its specific properties uncharacterized. It fell between measurements. Only took 13 billion years for the light to travel, and the burst lasted 8 seconds, and we missed it by having our detector in readout mode. The irony settles into the archive alongside the sparse data that does exist. The gaps will narrow. Future detectors will feature faster readout, shorter dead time. Future surveys will observe more sky more frequently. Gravitational wave detectors, operating continuously without dead time, will catch events that electromagnetic telescopes miss, but gaps cannot be eliminated entirely. Finite resources preclude continuous monitoring of all sky at all wavelengths at all times. Choices about where to point, when to observe, how long to expose. These choices create gaps, and into those gaps fall events, real, bright, detectable. Except for timing, the universe cares nothing for readout schedules, for weather, for telescope allocation committees. It proceeds with its explosions, its transients, its variations, indifferent to whether observers point appropriate instruments appropriately. Most events occur unobserved, even in the era of automated surveys, even with dozens of telescopes scanning the sky nightly. Most of the universe most of the time goes unwatched. The coverage improves each decade. The gaps narrow, but they persist. The stillness between exposures, the moments when detectors transfer data rather than collect it, the intervals when the universe continues while human instruments pause. In those moments, unrecorded supernovae, uncatalogued asteroids, undetected comets, events of every category. occurring in darkness. In the gaps between observation, the photons arrive, find no detector waiting, scatter into the environment. The universe maintains no records of unobserved events. Human knowledge contains no blank entries for event that occurred but was missed. Only the observed gets archived. The rest, silence. The detector completes its readout, begins the next exposure. And whatever occurred during the gap, if anything occurred, has already faded, already dispersed, already passed beyond reach. The universe keeps no record, maintains no buffer, offers no replay. It presents its phenomena once. Either observation coincides with occurrence, or the event passes unrecorded. The telescopes continue their sampling. The gaps persist between samples, and in those gaps, the stillness, the unobserved, the moments that happened but left no trace in human knowledge, the universe in the spaces between our looking. The detector cools slowly in the orbital night. Electronics settle into their thermal equilibrium, heat dissipating through radiators into the vacuum. The data has been transmitted. The pointing has been updated for the next target. For now. In the minutes between observations, there is only the patient hum of systems maintaining themselves somewhere below, hidden beneath clouds and atmosphere and the bright curve of Earth's limb. Observatories prepare for evening. Dome shutters will open. Mirrors will achieve final temperature stability. Autoguiders will lock onto reference stars. The night's observation sequence will begin, but not yet. For a few moments more, there is the waiting, the stillness between one observation and the next, in archives distributed across continents, stored in climate-controlled facilities and redundant server farms. Data rests, petabytes of images, spectra, photometry, the accumulated observations of decades, each file containing photons that traveled billions of years to reach silicon detectors, to liberate electrons, to become numbers in arrays. Some of those numbers have been interpreted, published, incorporated into models of galaxy evolution, stellar physics, cosmological expansion. They have done their work, answered their questions, joined the great edifice of human understanding. Others wait still, flagged as anomalous, classified as artifact, or simply unexamined, too faint for initial priority. Filed for possible future investigation that may or may not arrive. The photons that created them have long since been absorbed, converted to heat, dissipated into thermal noise. But their information persists, waiting, patient as only data can be patient. The universe continues its processes without pause. Stars fuse hydrogen. Galaxies merge across giga-year timescales. Neutron stars spin down. Black holes accrete. Comets sublime. Asteroids tumble. Most of this proceeds unobserved. The tiny fraction that falls within telescope fields of view. During exposure times, when instruments function properly, when skies are clear, this fraction gets recorded. The rest, darkness. Not darkness meaning absence of light, but darkness meaning absence of observation. The universe luminous with electromagnetic radiation. But unmet by detectors, the observatories will continue. New instruments will achieve higher sensitivity, broader coverage, faster cadence. The gaps will narrow, though never close completely, and in the data streams, glitches will continue appearing. Real events misclassified as artifacts, instrumental effects mimicking astrophysical signals, edge cases defying clear categorization. Each will be examined, classified, archived. Each will join the vast collection of observations, understood, mysterious, or ambiguous, that constitute human knowledge of the cosmos. The detector completes its thermal equilibrium. The next target coordinates load into the pointing system. Reaction wheels spin up. The telescope begins its slow rotation toward a new field. The universe waits there, as it has waited for billions of years. ready to be observed, indifferent to whether observation occurs. Photons depart distant galaxies. They begin their journey earthward, traveling at the only speed they know. Some will arrive during exposure time, some during dead time, some when clouds obscure, some when no telescope points their direction. The universe offers its light freely. Human instruments accept what they can, and in the archives, data accumulates. The glitches and the discoveries, the certain and the ambiguous, the interpreted and the waiting, all of it preserved, all of it available, all of it part of the patient work of looking upward, recording what appears, and trying to understand. The telescope settles on its new coordinates. The shutter opens. Photons begin accumulating in pixel wells. Somewhere, something is happening. A star varies. A comet fragments. An interstellar object passes. Perhaps this exposure will capture it. Perhaps it will fall into the gap. Perhaps it will be detected but misclassified. The universe proceeds regardless. Luminous, patient, indifferent, and the observation continues, one exposure at a time, sampling the cosmos in discrete moments, building knowledge from photons that traveled unimaginable distances to reach silicon and become data. The work continues. The mysteries persist. The archive grows. And in the stillness between exposures, the universe continues its ancient processes, observed or not, understood or not, glitched or clear, timeless, ongoing, infinite in patience,